In this lesson, we're going to look at how we can graph logarithmic functions. And before we do that, we're going to look at how to find the inverse of this exponential here. So if we have 3 to the x equals y, we should know from previous units that in order to find the inverse, the first thing we need to do is switch the x and the y. So we're going to make this 3 to the y equals x. Now our goal here is to solve for y and get y by itself. If we look at the original function, 3 to the x equals y, that is an exponential function. And from last class, we learned that the inverse of an exponential function is a logarithmic function. So let's take this new equation that we have, 3 to the y equals x, and let's convert it to logarithmic form. So we're going to write the word log. The base would be 3, and then we're going to say of x equals y. So the original function was y equals 3 to the x, and the inverse is y equals log base 3 of x. So we should know from doing inverses in the past that if we are looking at a graph of the original function and its inverse, that they are reflections over the line y equals x, and that any points that we have on one graph, the inverse will have the opposite points, meaning that the x's and the y's will be switched. So let's look at a graph of this. So this red graph is our exponential growth graph. This is 3 to the x. The green line is our reflection line of y equals x, and this blue graph is the inverse of the red graph, which would be log base 3 of x. So we can see that if we reflected the red graph over the green line, we would get this blue graph. If we pick a point on the red graph, for instance, this point here, which is 0, 1, on the inverse, we should have the point 1, 0, which we do here. If I pick another point, for instance, this point, which is 1, 3, I should have 3, 1 on my inverse graph, which I do. Okay, so just kind of a visualization of what the inverse is of a exponential, which is a logarithm. So let's get into details of this. So again, this is just a recap of what we just said. If you have a function and you graph its inverse, they're reflections over the line y equals x. Now this graph is just a random graph. It is not an exponential or a log. It's just a random graph here. So if I have the red graph and I reflect it over this dotted purple line, which is y equals x, the resulting graph would be this blue graph. So when we're doing graphing logs, basically we're going to be doing similar things to what we did with graphing exponentials, but because it's the inverse, literally everything is going to be opposite of what it was. So it's could be good, but it also could be confusing. If you know how to graph an exponential and that makes sense, just kind of think of the opposite of everything. So the first thing we're going to do is look at a basic log graph. So y equals log base b of x is your basic function. And we have two options that b can be. So just like with an exponential, right, our b, which is our base, could be greater than 1 or between 0 and 1. Now, when b is greater than 1, our exponential graph is a growth, and our if it's less than 1 or between 0 and 1, it's a decay. In this case, we don't really call them growths or decays. So I'm going to call this one, and we'll see what I mean here. I'm going to call when b is greater than 1, I'm going to call this down to up. And this will make a little bit of sense when we kind of get to this. So a couple things that are different about an exponential versus a logarithm. So in an exponential, right, we have a horizontal asymptote. So in a logarithmic graph, because it's the inverse, we're not going to have a horizontal asymptote. We are going to have a vertical asymptote. So I'm going to draw this dotted line here. So a horizontal asymptote was y equals 0. So a vertical asymptote, and I'm just going to write it out for the first time here, but I'm going to be abbreviating it as VA from now on. So vertical asymptote is going to be the equation x equals, in this case, 0. Now, will that change? Yes, it depends on what the function is, but for the basic log graph, we have x equals 0 as a vertical asymptote. Now, in an exponential graph, so I'm going to go ahead and just kind of sketch an exponential growth. So this is the growth graph from an exponential. So what we're going to be doing on this graph here is making the reflection of this over the line y equals x. So in an exponential, we have a y-intercept. So that means that in a logarithmic graph, we are going to have an x-intercept. So if I have an x-intercept, the y value has to be 0. So I'm going to put a 0 here. In order to figure out the x-intercept, we're plugging in 0 for y. So I'm going to break this over here. So if I plug in 0 for y, this is going to give me 0 equals log base b of x. And now I'm going to go ahead and change form. So I want to change this to an exponential. So I'm going to make this b to the 0 equals x. And b to the 0 is going to be 1. So 1 equals x. So my x-intercept is going to be 1, comma 0, which is going to be around here. Now this graph, we said, is going to be down to up. So if it's a reflection over the line y equals x of this exponential growth graph, our logarithmic graph is going to look something like this. And then from here, we can identify the domain. Now looking at the domain, what the x's are doing in this case, they're going to be greater than 0. So we're going to say from 0 to infinity. And then the range, because on an exponential graph, the domain is all real numbers. The inverse of that would be that the range of the exponential or of the logarithmic graph will be again all real numbers. So negative infinity to infinity. Now every single log graph has a range of negative infinity to positive infinity. The domain can change depending on how the graph moves, and we'll look at that in a little bit. So let's also just do the end behavior here. So our end behavior, our right end, as x is approaching, in this case, infinity, y is also approaching infinity. On this left end, x is approaching 0 and y is approaching negative infinity. So in an exponential graph, the x's were both going to either infinity or negative infinity, and the range, one of the sides, not the range, the y, excuse me, would go to, in one of the directions, would be going towards the horizontal asymptote. So now that we have a vertical asymptote, one of the x's is going to go towards that vertical asymptote. Now when b is between 0 and 1, this graph is going to be what we call, or I call, up to down. So it's going to be similar to that decay. So I'm going to go ahead and draw. This is our exponential decay graph, something like that. So now if I reflect that over the line y equals x, that's going to give us our log graph for where b is between 0 and 1. So again, it's very similar to the other one. So it has a vertical asymptote. I'm just going to put VA of x equals 0. If I solve for the x-intercept the same way, here I'm going to have the same x-intercept of 1, 0. Go ahead and put that here. But now we're going up to down. So our graph is going to look something like this. And again, our domain will be similar to the one we just did, from 0 to infinity. And again, notice that we have a parenthesis on the 0 because we can't include it since it's an asymptote. And then our range for every single one of these will be negative infinity to positive infinity. So these are the basic graphs of a log. So now we're going to look at how they transform. So these slides are very similar to the exponential graph slides that we had. Okay, so first we have translations and shifts. And just as a quick note, all of these are examples using b greater than 1 for the log. Obviously, if b was between 0 and 1, the shape of these would be a little bit different, but the same idea. Okay, so with translations and shifts, we have movement up, down, left, or right. And the little note on the bottom is the complete opposite of what it was for an exponential. So translations may change. In the exponential, it said the y-intercept. But now with a log, we have the x-intercept can change. With the exponential, we had that the range could change. But now with the log function, we have that the domain can change. And in the exponential, we had the horizontal asymptote could change. And in the log, we have that the vertical asymptote could change. So let's look at when it moves up. So just like every other function that we've looked at, if something is moving up, that means that we're having something added outside of the function. So notice this plus c here. that means that the graph is moving up a certain amount. Now, if the graph is moving up, we can see that the vertical asymptote has not shifted. It's staying at x equals 0. So in this case, vertical asymptote would be x equals 0. Okay, the x-intercept, I'm still going to plug in 0 for y. So I'm going to write this up here. If I make 0 y, I have log base b of x plus c. In order to change this to an exponential, I need the log to be by itself. So right now the log is not by itself because there's a plus c. So if I subtract c from both sides, I'll get negative c equals log base b of x. Now I can change forms because the log is by itself. So we'll say b to the negative c is equal to x. So our x-intercept would be b to the negative c, comma 0. The other thing that can change, now for these problems, I'm only doing the things that might change. So the domain will be 0 to infinity. Okay, that didn't change because the graph moved up, which didn't affect the vertical asymptote changing. Okay, if we look at it moving down, same idea. So if it moves down, we're going to have a number subtracted outside the function. Because it's moving down, it's not going to change our vertical asymptote. So again, this is going to be x equals 0. The x-intercept here, again, if I plug in 0 for y, the only difference here is that I'm going to add c to the other side instead of subtract it. So I'm going to have b to the positive c, comma 0. And then again, our domain will be 0 to infinity. Now, when we had exponentials, when we moved it up and down, that changed our horizontal asymptote because that was in the y direction. So now we're moving up and down. It's not changing our vertical asymptote. Let's look at moving left. So if we're moving left, we're going to add a number to the x, like inside the parentheses. So if a number is added, it moves to the left. If we're moving the graph to the left, you can see that the vertical asymptote has now shifted left. So our vertical asymptote will be x equals negative c. So even though it's a plus c here, that means it's moving to the left. If it's moving to the left, then it is going to be negative because it's moving in the negative direction. For the x-intercept, again, I will be plugging in 0 for y. So 0 equals log base b of x plus c. Now the log is by itself. There's nothing added or subtracted outside. Even though there's a plus c inside, it's part of the log. So I can go ahead and change forms. So I'm just going to keep going up here. B to the 0 is equal to x plus c. So if I want to get x by itself, b to the 0 is 1. So x plus c, get x by itself, subtract c. So I end up with x equals 1 minus c. So my x-intercept will be 1 minus c, comma 0. And then the domain, because this graph has shifted left c amount, my domain would be negative c to infinity. And then moving to the right, we're subtracting something to the x inside the parentheses. So everything is shifting to the right, meaning that the vertical asymptote will also change. So our vertical asymptote will be x equals c. The x-intercept, very similar to when it moves left. The only difference is that because it's a minus c, we're going to have to add the c. So this will be 1 plus c, comma 0. And the domain, in this case, will be c to infinity. Now, if it doesn't make sense with the B's and the C's and all that stuff, it's fine. When we put numbers in here, this will make a lot more sense, but these are just like the basic kind of movements and what's happening to the key features of the graph. Okay, and then just like with exponentials, the other type of transformation we're going to see is a reflection, and there's two reflections. We can have a reflection over the x-axis, in which there will be a negative in front of the word log, or a reflection over the y-axis, which will have a negative attached to the x inside. Now, similar to the exponential graph, when we had an exponential graph, when it was a reflection over the y-axis, the graph changed from being a decay to a growth, or a growth to a decay. So the shape of the graph switched. In this case, because this is the inverse, that's going to happen when it reflects over the x-axis, and that's what you'll see a note here for. So we don't really call them, again, growths or decays, but if we have like a down to up, and it reflects over the x-axis, it will become an up to down and vice versa. So again, both of these examples are when b is greater than 1. So I'm going to go ahead and just draw in the regular function first on both of these. So you can these are pretty bad, but so the green graph here is a regular log when the base is greater than 1. So it's a down to up. If it reflects over the x-axis, it's reflecting this way, it becomes an up to down function. If I have a reflection in the y-axis, I'm reflecting it over the y-axis, so it's just going to be a straight reflection in that direction. So it's not going to change its shape. It's still going to be, in this case, like a down to up. It's just going to be reflected over the y-axis. So I'm going to just erase this so we don't get confused for 1 second. Okay, so again, similar to the exponential, we will change the shape, but in this case, it's going to be if it's a reflection over the x-axis. So now let's look at a couple of examples. So just like with exponentials, we want to identify a few key features. We want to identify the base to figure out what shape it's going to look like. We want to identify any types of transformations. Then we need to find the vertical asymptote and the x-intercept in order to graph it. And then we'll fill in the graph and identify the other pieces of information. So the first thing we notice about number 1 is the base. Now this base is 3. 3 is greater than 1. So that means that this will be a down to up function. Then we look for transformations. So we have a negative here in front of the x, which means that this is a reflection over the x-axis. The y-axis, my bad, excuse me. Because it's reflecting over the y-axis, it is not going to change the shape, so it's not going to make it up to down. It's going to stay down to up. And then this +1 is going to move the graph up 1. So we can go ahead and identify some information. Since this graph is not moving left or right, the vertical asymptote will not change. So it will stay x equals 0. So I can go ahead and put my vertical asymptote here. The x-intercept, I'm going to plug in 0 for my y. So I'm going to do that over here. So 0 equals log base 3 of negative x plus 1. So before I can change forms and make this an exponential, I need to isolate the log. So I need to subtract 1. So negative 1 equals log base 3 of negative x. I can now change forms. So this is 3 to the negative 1 equals negative x. 3 to the negative 1 would be 1/3, and that's equal to negative x. So that means x equals negative 1/3. So my x-intercept is negative 1/3, comma 0. And negative 1/3 is going to be to the left of the vertical asymptote. So I'm just going to draw a dot here for that. And now we can go ahead and graph this. So we know that it is a down to up function. So I'm going to just real quick draw on this side. The normal function of this looks like this. So I'm taking this graph and I'm reflecting it over the y-axis. So that graph will look something like, like that. So I'm going to get rid of the green so we don't get confused. So then from here, we're going to identify the domain. So our domain here is going to be negative infinity to 0. Our range will be negative infinity to positive infinity. And we're going to do our end behaviors here. So on the left end, x is approaching negative infinity and y is approaching positive infinity. On the right end over here, x is approaching 0 and y is approaching negative infinity. Okay, so let's look at the second example. So we have a base of 2, which again means that this is greater than 1. So our graph will be a down to up graph. We have a negative in the front, which means it's a reflection over the x-axis. Because it's reflecting over the x-axis, this does change it, so it's going to makes it up to down. So instead of being a down to up function, it will change to an up to down function because of that reflection. And then this plus 3 is going to move left 3. So we have our vertical asymptote. Because this graph is moving 3 to the left, our vertical asymptote would be x equals negative 3. So I'm just going to draw that asymptote here. Okay, for the x-intercept, we're going to plug in 0 for y, and I'm just going to do that right here. I'm going to erase what we had from before. So if you need this, just rewind the video. So I'll plug 0 in for y, and I have negative log base 2 of x plus 3. Now, the log looks like it's by itself, but it's not because of the negative in front. So we want to divide both sides by negative 1. 0 divided by negative 1 is just 0. So I have 0 equals log base 2 of x plus 3. So now we can change forms. 2 to the 0 equals x plus 3. 2 to the 0 is going to equal 1. So 1 equals x plus 3. If I subtract 3, x equals negative 2. So our x-intercept is negative 2, 0. Since my vertical asymptote is at negative 3, negative 2 is going to be to the right of that. So we're here. And now we had a down to up function, but because it reflected over the x-axis, it is now an up to down function. So it's going to look like this. Oops, pretend it goes through that point, and it looks like that. Oh, this is not pretty, but there we go. So our domain will be negative 3 to infinity, and our range will be negative infinity to positive infinity. If we do our end behavior, our right end, x is approaching positive infinity, y is approaching negative infinity. On the left end, x is approaching negative 3, and y is approaching positive infinity. Okay, we're going to do this last example. So again, first thing to do is identify the base. So here our base is 0.5. So that means that it's between 0 and 1. So this will be up to down. Okay, and then we have this minus 1 on the inside, means it's going to move right 1. And this minus 4 means it will move down 4. Okay, so since this is moving to the right, that means the vertical asymptote will change. So if it's moving 1 to the right, our vertical asymptote is x equals 1. And I can go ahead and draw that vertical asymptote here. Okay, for the x-intercept, again, I'm going to plug in 0 for my y. So 0 equals log base of 0.5 to the x minus 1 minus 4. So I have to add 4 to get the log by itself. Now I can change forms. So 0.5 to the 4th equals x minus 1. So we could think of this one of two ways. You can use a calculator because we have a decimal, or 0.5 is just 1/2. If I raise 1/2 to the 4th power, this is going to give me 1 over 16 equals x minus 1. And if I add 1 to that, I'm adding 16 over 16 to 1 over 16. I get 17 over 16. And that should be about like 1.03 or 63 or 3 something. So if you do it as a decimal, that's fine. I'm going to keep mine as a fraction here. So that's going to be 17 over 16, comma 0. So that's more than 1. So that dot's going to go about here. And then it did not change, so it's going to be an up to down function. So we're going to start up, and then we're going to go down. Okay, our domain will be from 1 to infinity. Our range will be negative infinity to positive infinity. And then let's do our end behavior. So our right end, x will be approaching positive infinity. Y will be approaching negative infinity. On the left end, x will be approaching 1, and y will be approaching positive infinity.